Well, hello everyone and welcome to Lecture 7 on the Material Science and Engineering course. In the last session, or for the last couple of sessions, we've looked at what happens when you place metals largely under some kind of load, and we focused on tensile load. We've looked at a number of properties that can be used to describe the behaviour of the material under such tensile load. We've looked at yield strength, tensile strength, and indeed the fracture point. We've also looked at the failure of materials. So how can we think about failure in materials? We've looked at various types of fracture mechanisms. We've looked at fracture mechanics. In today's session, I'd like to give a recap of dislocations within crystalline materials. So we've had a look at some of these already, I think in lecture 3 or 4, and I would like to go back over some of these ideas. I'd then like to consider how these dislocations within a material can move under an applied load, and we term this slip. And I'd like to spend the end of this session by talking about ways in which we can strengthen metals. So techniques that we can use to strengthen materials and perhaps delay the onset of fatigue and creep and other failure mechanisms. So we spoke about dislocations. We spoke about the idea that they are line defects within a material. And slip between crystal planes when they are under load occurs as a result of the movement of these dislocations within a material. And if things are moving, if atomic lattice sites are moving about a material and bonds are breaking, then we produce permanent plastic deformation within the material, right? We start to break bonds. We're no longer talking about just stretching bonds or putting them under pressure in that respect. We're talking about breaking bonds and allowing planes within a crystalline material to slip, and ultimately this is a definition on the atomic scale at least of plastic deformation. To remind you then about an edge dislocation, this is where we have an extra half plane of atoms within the crystalline material. So you remember these are a form of impurity within our material. And we can define the extra half plane then by something that we call a Burgers vector. So the Burgers vector will always lie at an angle that is perpendicular to the dislocation line itself. So the dislocation line runs throughout the material. You can see there's an extra half plane of atoms in both of those schematics there. And the Burgers vector will lie at a perpendicular angle to that. Now, the result of having an extra half plane of atoms in the material is that it stretches and distorts the lattice to some extent. And we can define the direction and the magnitude of that lattice distortion by using this idea known as the Burgers vector. So the key thing there, I think, is that there's an extra half plane of atoms within the lattice somewhere, and that creates local distortion and is likely to put the various regions of the lattice under compressive and tensile strain. Now, you can actually image these things if you have an electron microscope that is powerful enough, and I show you there a TEM image of an edge dislocation. The bottom right image is probably the easiest to observe it in. You can see that there's the black lines highlight the amount of lattice mismatch that occurs because of the insertion of this extra plane of atoms. And in fact, the image at the top there is a less zoomed in image, if you like, panned out image, and it highlights the fact that there are lots of edge dislocations throughout this material. Now, when you apply a stress to a material like that, these edge dislocations can migrate, and they do so in response to an applied stress. And what happens is when that crystalline lattice is under shear or an applied tensile load, the dislocation hops along and it moves through the material. And essentially what it does is it hops one unit step, one sort of lattice unit step, as the stress increases. Now we'll talk in a couple of slides' time about whether or not this makes sense given our fairly simple model of metallic bonding. So there's a nice little cartoon of what's happening here. For this edge dislocation to move, it requires the successive bumping of half planes of these atoms. The bonds across the planes that are slipping then are broken and remade in succession. And when we stretch a material, we apply energy to it, right? So the very fact that we're applying energy through the form of a load allows this movement to happen. It allows these bonds to break and reform. You know that we also spoke about a screw dislocation. So here our Burger's vector and dislocation line are parallel to one another. On the left there I show you something that exhibits perfect crystalline order, and on the right is the same system but something that has been subjected to shear stress. Now this process by which a dislocation moves through the crystal lattice is called slip, and the direction that it moves in is called a slip direction, and that movement points in the direction of the Burger's vector. Now when we consider this from the perspective of a metal, this slip or this movement of these dislocations throughout the material explains why the strength of a metal is much lower than if we just considered the strength of the individual metallic bonds that make up the material. If there was perfect order within the material, then we would have to break all the bonds along the cross-section of a material. So for an iron bar, for example, this might include applying loads of sort of 7 to 10 gigapascals. But instead, plastic deformation occurs as a result of slip, and therefore only a smaller fraction of bonds must be broken. Now, for the same reasons, this movement and the absorption of energy, if you like, as we apply a load, gives metals some of their inherent ductility. Now, this is an interesting fact about the density of these dislocations within a metal. The dislocation density of some of the softest metals, so dislocation density is the length of dislocations per unit volume. In some of the softest metals, that can be around 10 to the 6 centimeters per centimeter cubed. And you can get, if you deform the material and you allow plastic deformation to happen, then you can get densities of up to 10 to the 12 centimeters per centimeter cubed. That distance is roughly the distance as the crow flies from the Parkgate Road campus in Chester to the Thornton Science Park. That tells you then that metals are absolutely jam-packed with these dislocations and line defects. Now let's think about these dislocations with respect to the kinds of materials we're talking about. Well, there are lots of them in metals, And motion, the dislocation motion, is much easier in a metal because of the type of bonding that exists. I guess it's a kind of form of ionic bonding. It's not the ionic bonding that we spoke about with sodium chloride as an example. We think about it as a sea of negative charge and islands of cationic charge, which correspond to the metal nuclei. The reason why this kind of slip motion in metals is much easier then is because the bonds themselves are non-directional. In a covalent compound, so something like a ceramic or a polymer, dislocation motion is much more difficult because with a covalent bond, you have some directionality to the bond itself. And indeed, in an ionic substance, so something like sodium chloride, dislocation motion is difficult because that system is composed of ions of negative and positive charge which reside next to each other in an alternating fashion. And if you start to gain slip in those systems, then suddenly you're going to have like charges next to each other, and that becomes energetically unfavourable. So let's consider our edge dislocation again. As that edge dislocation moves through our slip plane, there are going to be regions of compression and tension present. And indeed, there's strain in the lattice around any given dislocation, regardless of what it is. Above the Burgers vector, then, the lattice is under a compressive strain because you've squeezed an extra half plane of atoms into the lattice, and that makes everything much more tighter. And below the Burgers vector, the lattice is under the local region around that dislocation is in a state of tension, as it has to bend around the extra half plane. Now, as the load is applied and these materials start to slip, as these dislocations move through the material, just like charges, like strains will repel one another. So compressions are not going to want to move towards another compression because this would just generate greater compression. And tension is not going to want to move towards tension because that creates greater tension in the region around two dislocations that are moving towards each other. However, opposing strains will want to move towards one another. So in a slip system, compression will want to move towards tension and vice versa, because what this does is it relieves the stress, whether that be compressive or tensile, and lowers the energy state of the system. And ultimately, when opposing strains reach each other, they very simply annihilate. You can imagine two half planes on either side of their respective Burgers vectors. As they move towards each other, those two half planes just end up bonding, and you annihilate any compression or tensile strain that's experienced in that local region of the lattice. Now, you can see this, and I urge anyone to download this paper from Applied Physics Letters, because you can see two edge dislocations moving towards each other in this series of transmission electron microscopy images. So on the left there is highlighted two edge dislocations on either side of their respective Burgers vectors, and the two right-hand images are at 120 and 180 seconds respectively, and you can see that they move closer to one another until they eventually meet and they annihilate each other. Okay, so can we use some of the concepts that we've learned over the last few lectures to strengthen materials, to make them stronger for the applications that we need to use them in? And there are four strategies for strengthening. I'm going to speak about three of them today. We'll speak about the fourth in some detail next semester. The first is to reduce the grain size. The second is to form solid solutions, and the third is to use precipitation strengthening. So what happens when we reduce the grain size of a material? Well, those grain boundaries themselves are actually barriers to slip. And you'll remember we spoke about an angle of misalignment or an angle of misorientation at a grain boundary. The larger that angle of misorientation is, the greater the barrier strength to slip is. So if we reduce the grain size of a material, then we essentially create more barriers to slip. That edge dislocation can't move throughout the material and it becomes stronger. That doesn't necessarily mean that's what we want. If strength is what we're after, great. But remember, if we inhibit that movement through slip, then we inhibit the material's ability to undergo plastic deformation and we essentially make it less ductile. So it's a trade-off here between ductility and strength. And there's a well-known method for strengthening a material by reducing the grain size, and it's governed by an equation called the Hall-Petch equation. And it relates the yield strength of a material to a value, the yield strength value before the grain size is reduced. And you can see the equation on the left there. It considers the diameter of grains. Ultimately, smaller grain size means a higher yield strength. We can also form solid solutions. So we can add impurity atoms with the aim of strengthening a metal. And these impurity atoms themselves cause some kind of distortion in the lattice. They do create lattice strains, but it's these strains themselves added by these impurity atoms that can act as barriers to dislocation motion. What we're doing here is essentially creating localized compressive and tensile strain around the impurity atom. And by creating those, we create regions of the lattice that are likely to repel one another and don't move towards each other. Now, another way of thinking about this, another way in which small impurity atoms can strengthen materials, small impurity atoms will tend to concentrate at dislocations on the compressive stress side, so above the Burgers vector. Remember that they're very mobile. They're not likely, this is where they are likely to concentrate. If they accumulate on this side of the Burgers vector, they relieve some of the lattice stress. And this lower energy of the system that's created by this means that the dislocation is essentially harder to move. So they accumulate on that side of the Burgers vector, they lower the energy of the system and they make it harder for the edge dislocation to move. Similarly, then, we can incorporate another mechanism through which larger impurity atoms can strengthen materials is the notion that they like to accumulate on the lower side of the Burgers vector, as it's shown in that diagram. They tend to concentrate on the tensile stress side of dislocations. What they're acting to do here then is essentially fill gaps in the lattice that is caused by this tensile stress. And again, the fact that they're filling these gaps lowers the energy of the system, and these edge dislocations become much harder to move. What they're doing essentially is pinning the edge dislocation in place. And you can see there that this is an example of solid solution strengthening in copper. So the two graphs there are for tensile strength and yield strength of copper with nickel added. And you can see that from 0 to 50%, you increase the tensile and the yield strength of copper as you add nickel. And it's for these exact reasons that these impurity atoms are filling gaps essentially and pinning edge dislocations in place. Now you can also use precipitation strengthening, and this is accomplished by phase transformations that are introduced by a heat treatment, and we will cover this rather in a lot more detail next semester. We're going to go into some very deep detail about heat treatment of steel next semester. But what we're doing essentially is we are heat treating metals. We encourage the formation of new phases. Okay, so basically we're heating them and cooling them down, and we gain small particles of a new phase, which we call the precipitated phase, and they are acting as barriers to slip in much the same way as grain boundaries or impurity atoms do. And these are used heavily. It's used in the aviation industry for aluminium alloys, and I'll show you there a TEM image of some precipitates in a copper aluminium alloy. Okay, so the final method of strengthening a material is called strain hardening. And we're going to discuss these concepts in much more detail next semester, but we'll introduce it here. We briefly considered this at the end of the last lecture when we were talking about creep strain. And you'll remember that there's this kind of preliminary region of the creep strain graph by where the creep strain rate slows because the material is experiencing hardening under an applied load. Well, this is the concept that ductile metals can become harder and stronger as they are plastically deformed. So what we're doing with strain hardening, or cold work as it's called, is we are plastically deforming the material to make it harder and stronger. The reason why it's called cold working is because we're working at a temperature which is far below the melting point of the metal in question, and all forms of cold working will act to plastically deform the metal by reducing its cross-sectional area. You can forge metals, you can compress them between a die, you can draw them through narrow orifices by, you see on the bottom left there, either drawing them or rolling them, or you can extrude them, you can force them through another orifice with pressure. All of these act to plastically deform the metal and make them harder and stronger. So how do they do that? Well, as we plastically deform the material, those dislocations which are already present in the metal start to entangle with one another. We also form new dislocations by compressing the material. And on average, if we think about those diagrams by where we were looking at dislocations repelling one another, on average, those dislocations repel. So the dislocation becomes much more difficult. By introducing more dislocations and causing them to entangle with one another, suddenly we pin them in place and they're much more difficult to move. Now, the result of cold work is that the dislocation density increases. So they entangle with one another more and they become stronger and harder. If you want to reverse the impact of cold work, then you can heat treat the material, and that reduces the dislocation density. And again, we'll talk about this in much more detail next semester. Have a look at the impact of cold work then. You can see that in all cases, the yield strength, the tensile strength increase, but the ductility decreases. So as we strengthen this material, you reduce its ductility. And that makes sense because with cold working, with precipitation hardening, with solid solution forming, in every case, we're pinning edge dislocations in place and we're stopping the movement of these things throughout the material when it's under an applied load. We make them stronger and harder, but of course, we limit the ability of the material to plastically deform, to absorb energy under an applied load. So the ductility decreases. And I show you here some values for the yield strength, the tensile strength, and the ductility for a copper, which has had cold work of 35.6%. The yield strength increases, the tensile strength increases, but look at the huge reduction in ductility for the material. So if we want to increase the strength of the material, we have to make sacrifices elsewhere. And of course, here we're going to make sacrifices in ductility. Now, sometimes once we've cold worked a material, we might want to get rid of some of the effects of that cold working. We might want to recover some ductility of the sample. So here we need to think about then reducing slightly the dislocation density. And the way we do that is to put it through a heat treatment. We call that annealing the material. If we place a material through a heat treatment, we raise its temperature and then cool it slowly at a defined rate, then the tensile strength of the material starts to decrease again, but the ductility increases, i.e. we've basically nullified the effects of cold working. And there are three stages to this annealing process. There's a recovery stage, a recrystallization stage, and a grain growth stage. The first then is the recovery stage, which is when we really start to reduce the dislocation density by annihilation. This entirely results from diffusion. So we're heating the system up, we're allowing diffusion to occur, and we're actually encouraging those slip planes to move. And if they move, then they're able to annihilate one another. And that leads to a reduction in dislocation density. There's then a recrystallization stage. So as we cool the material down, it will start to recrystallize. And this will then form new grains that have lower dislocation densities relative to the cold worked metal. They'll be much smaller in size, and they will consume and replace the parent cold work grains. And eventually then all of those cold work grains are consumed and replaced. And you can see the image on the left there is at 4 seconds after the recrystallization process has happened, and the image on the right is 8 seconds after the recrystallization process has started. The large grains in the image on the left, you can see them as kind of striated, very large patches, are the cold worked grains that are slowly being consumed and replaced by this new recrystallized grains that will have a lower dislocation density. You can see after 8 seconds, they're basically entirely replaced with grains that are smaller in size. Now, if you leave this for even longer, so this is the grain growth stage, the average grain size will start to increase. Those small grains will kind of shrink away and be consumed by larger ones, and those larger grains will continue to grow. The reason why they grow is you can think about it from a thermodynamic perspective, because large grain boundaries rather have an increased energy state, so the system will try and grow them to some degree in order to reduce the grain boundary area. But remember that these new grain boundaries that have grown have a lower dislocation density. The first graph here is a plot of tensile strength and ductility against the annealing temperature. It shows you the influence of the annealing temperature on the tensile strength and ductility of a brass alloy after just 1 hour of annealing time. The recrystallization temperature is shown on there as the dashed line. So this is the temperature at which crystallization just reaches completion in 1 hour. And it shows that the grain size increases as the annealing temperature is increased. Okay, so I will leave it there. This is the last lecture that you will receive from me before the Christmas holidays. So I wish you a very Merry Christmas, and I wish you a safe and happy holidays, and I will see you in the new year.